Thank you, Hung. So first, I'd like to thank Hung for the kind invitation. It's my great pleasure to give the talk online, and I wish I can meet all of you at some point in person. So today I'm going to talk about the incompressible porous media equation, which is a fluid equation that many of you are probably not familiar about because it's not as popular as, let's say, Euler equation or the SQG equation. So I'm going to first start with an introduction about that. And I'm going to focus on the small scale formation aspect of this equation. And this is the joint work with Alexander Kiselev. So let me start with a quick introduction on what is the incompressible porous media equation, which I will abbreviate as the IPM equations throughout the talk. So the idea is that we have some kind of density of incompressible fluid rho, and rho is transported by some velocity field u, which we require it to be incompressible. Okay, and so in that case, the equation for rho is simply this transport equation, and then u being incompressible means that the divergence of u is equal to 0, right? So for the spatial domain, I'm going to assume that this is a two-dimensional equation. So omega is either the full plane or it's a two-dimensional periodic torus, or it can also be a periodic strip where it is periodic in the horizontal direction and has two boundaries in the vertical direction. Okay, so many of you are familiar that, well, for the incompressible Euler's equation, it basically says that if you are following a fluid particle, then it satisfies the Newton's law that the acceleration is proportional to the force. Right. However, we are talking about the density of fluid in porous media here, and they behave in the way that instead of Newton's law, so these fluid particles, they do not have inertia, so they satisfy the Darcy's law instead. That is, at each moment, the velocity field of a fluid particle itself is directly proportional to the total force at that point. Okay, and here the proportionality is the constant is mu over kappa. Their physical meaning is the viscosity and permeability, which I'm going to set them to be equal to 1 just for convenience. And let's have a look at the force term. So we are assuming that the gravity direction is pointing down, which means that, well, for my density rho, at each fluid particle experiencing the gravitational force that is going downwards with the gravitational constant g, and then so it is the 2D vector where the second component only is the second component is there, right? Because it's a downward force. However, this is the gravitational force itself, but that is not an incompressible field, right? Recall that our requirement is that the velocity field at each moment has to have a divergence 0. And for that reason, we need to have an additional pressure term. So the use of the pressure term is that, well, this is the pressure term that makes U to be a divergence-free vector field. Okay, so in that sense, just like in the incompressible Euler equation, P itself is not explicitly given, but it is the function that makes the divergence of U to be equal to 0. And actually, P can be explicitly solved by taking the divergence on the both sides so that we would get Laplace P is equal to something that depends on rho. Right, and then we are able to inverse the Laplacian to find P and then plug that P into this expression to find U explicitly. So if you do that computation, which is the short computation, one will see that, well, once at each moment the density rho is given, then the velocity field U is determined by that density. So their relationship is called the Biot-Savart law. And so the relationship is as follows. So one first take the inverse Laplace of rho, and then take the grad perp, And on top of that, we take the partial derivative in the horizontal direction. Okay, so that may look a little bit strange to you at the very first glance because, well, it seems like this equation is more special in the vertical direction. But actually, this is because once we apply the divergence on both sides and then solve for P, so there will be some cancellation that is happening between these two terms. And after the cancellation, it turns out that we have a partial x1 term that is left. Okay, so this is it's not too hard to find. And just to give you some intuitive feeling of what the velocity field look like, I'm here drawing a picture of, let's say, suppose we have the density that looks like this in R2. Suppose my density rho is equal to 0 everywhere. So notice that it doesn't mean vacuum, right? So density itself is everywhere. You can think about rho as, because you can think about you add a whole constant to this rho. So we are using 0 as like the default density. So let's say the density is 0 everywhere else, and then there is a blob of liquids that is heavier than the average, and there is also a blob of liquids that is lighter. So throughout the talk, I'm going to use red to denote the heavier fluids where the gravity force is like more strongly pointing down, and then blue as lighter fluid where the gravity is pointing upwards. Okay, so if the only force is this gravitational term, then this part wants to go down and this part wants to go up, and the other terms, the other places want to stay still. But this force is not a divergence-free vector field, right? So after we correct it by gradient P to correct it into a divergence-free vector field, it turns out that there will be this this correction here in this direction, and that's what the velocity field look like. And one can also think about, well, if we are having just rho is one single delta function, then what is the velocity field generated by that? Here I am sketching a picture. So for a single delta function right here, so the streamline of the divergence-free vector field looks like this. So these velocity fields are pointing downwards and then downwards here, and overall this is still a incompressible velocity field. Okay, so that is the incompressible porous media equation and the Biot-Savart law. And next, I would like to compare a couple equations. All of them are set up in 2D, and they all have the structure that there is some kind of scalar function that is transported by a velocity field u that is incompressible. Okay, of course, we don't always name the scalar to be rho. Like for the 2D Euler equation, that scalar is actually our vorticity, which we would usually name it to be omega, but the name of the variable doesn't really matter, right? So we have these three equations to the Euler, the surface quasi-geostrophic equation, and the 2D incompressible porous media equation. All three of them takes the same form. There is a scalar valued function rho transported by an incompressible velocity field u. So what is the Biot-Savart law of u? How does u depend on rho? Well, for 2D Euler, we know that the velocity can be recovered from the vorticity by first taking the inverse Laplacian and then take the grad perp. Right, so if we are looking at its Fourier symbol, then the inverse Laplacian give us k to the -2 and then k perp for the grad perp, right? So in that sense, the symbol has the power -1, which means that, well, the Biot-Savart law of u is like one more derivative better than the scalar rho itself. Right, and as for the SQG, well, the difference between SQG and 2D Euler is that instead of taking the full inverse Laplacian, we only take a 1/2 inverse Laplacian. So there is one less integral in some sense, and that's also reflected in the Fourier symbol. So this is homogeneous of degree 0. And one can also see that it's roughly, we take only one derivatives and one integral, right? So u is roughly at the same regularity as rho. And what about IPM? Well, we just discussed that this is the Biot-Savart law for the IPM. We are taking one inverse Laplacian, which is two derivatives better, and then we take one derivative and another one. So again, U is like the same regularity as rho, so which is also reflected in the fact that the operator for the Fourier transform is homogeneous with degree 0. Right. So now we are seeing that both of these two symbols have degree 0, but they are not the same. Right. So one of the key difference is that this one is odd in terms of k, but that one is even. So it turns out the oddness versus evenness actually plays an important role in the well-posedness theory for these family of equations, which I will review soon. So in terms of the local well-posedness, so here I like to think about classical solutions. So I don't really work on like the local well-posedness on the borderline spaces. So let me say that for HS in sufficiently large S, the local well-posedness for all these three types of equations are well known. But when it comes to the global well-posedness, for 2D Euler, it's well known that the smooth initial data remains smooth forever, but that is the open question for SQG equation. And actually, if the power here is changed to anything between Euler and SQG, that's also an open question. And for the 2D IPM, the global well-posedness is also open. Okay, so let me briefly review the previous well-posedness results for the IPM. So the Cordova, Gancedo, and Orive has established the local well-posedness of IPM in HS for S bigger than a certain number. And they have also established certain blow-up criteria. So some of the blow-up criteria are more standard. For example, if gradient rho has its L infinity norm bounded, then the solution will remain HS for all time. And there are also some other blow-up criteria that they established to has more geometric flavor. So namely, they look at the level sets of rho, and then they show that as long as the level sets of rho are not too oscillatory, and then the Riesz transform remains finite in this integral, then the solution cannot blow up. Okay, there is other than the IPM itself, one can also tweak the Biot-Savart law to make it more singular. So namely, instead of taking the full inverse Laplacian, we can make the power here to be less than bigger than -1 by adding a beta to it. And Freelander, Gancedo, Sun, and Vico has showed that this more singular equation is actually U-posed as soon as beta is bigger than 0. Okay, so this is actually a sharp contrast with the SQG equation, because for the SQG equation, so we are taking half of the inverse Laplacian and then the grad perp. One can also tweak the Biot-Savart law to make it more singular. So to take the inverse Laplacian to be less than 1/2. And in that case, it's actually known that the equation is locally well-posed. So even though in terms of the order of the differential operator, it will be the same order as this one. Okay, so the reason that for these two operators of the same order, one is ill-posed and one is well-posed, is actually has something to do with whether this operator is even or odd. But they have shown that so the equation is ill-posed in HS, but actually the patch solution is locally well-posed for a certain range of beta. So to my best knowledge, the only global well-posedness of this equation is established in the perturbative regime when the initial data is close to certain steady state. So Al-Gindi has studied the steady state minus x2. So this is what the steady state look like. So it has the density is linearly changing in the vertical direction. And it's the stable one, which means the lighter fluids are on top and the heavier fluids are at the bottom. Okay, so he shows that he shows that this kind of steady state is asymptotically stable, and that directly implies if you do a sufficiently small perturbation, you will have global existence, and you will be converging to the steady state in HS for S that is large enough. Okay, and also another result by Castro, Cordoba, and Lear so considered the stability for where the domain is a strip where it is periodic in the horizontal direction and has two boundaries in the vertical direction. And they showed that here the stratified solution is still minus x2, but in this case, it will no longer be a global attractor because you may be converging to something that is not exactly the steady state, but closely, another stratified solution that is very close, right? Because now you have these two top and bottom boundaries. They show that, well, if one perturb it in sufficiently high HS class, then such perturbation will lead to a globally regular solution. So these are the only global well-posedness results for this equation so far. Okay, so and what about numerics? Like, what do people think, whether they guess whether there's a blow up or not? The work by Cordoba, Gancedo, and Orive has done extensive numerical simulations, and their simulations suggest that it seems like the gradient rho can be growing to infinity as time goes to infinity, although they have no evidence for finite time blow up. Okay, so for a typical profile, this is what the evolution looks like after a long time. So here, this direction here is x2. And one can see that as time goes on, it seems like the profile is getting closer and closer to a horizontally stratified profile, right? Although at certain places, the gradient of rho, they show that, well, it seems to be growing, but they have also compared the solution against their blow up criteria, and they don't think the solution is blowing up in finite time. Okay, so for us, we are not able to show whether there is a global existence or finite time blow up for a generic smooth initial data. That seems to be still a very challenging question out of reach. So together with Sasha Kiselev, what we aim to show is that assuming there is a global in time solution in a certain domain, let's say the torus or the strip or R2, we want to rigorously prove that gradient rho will really be growing to infinity as time goes to infinity. Okay, so it means that, well, if there is a classical solution for all time, then gradient rho will have at least that kind of growth. And if there is no global well-posedness, then gradient rho will only have a more dramatic growth, but because it will have a finite time growing to infinity, right? So it means that, well, for the solution during its lifetime, the gradient rho, we will show it at least have a certain kind of growth. Okay, so for these kind of small formation results, there has been quite a few of results of such flavor for the 2D Euler equation and also the SQG equation. So before I talk about our proof strategy for the IPM, let me just briefly review these results for the Euler and SQG. These kind of results can be traced back to Udovich, where he showed that the gradient of vorticity can have some infinite in time growth. And Nadirashvili showed that so when the domain is the annulus, there can be linear growth for all time. And so there has been some recent breakthroughs on the small scale formation in the past decades. And these results are more or less based on the important steady state that is discussed by Bahuri and Shimon. So this is what the steady state look like. It is a steady state in the torus where the omega is simply +1 and -1. It has this checkerboard structure. So such kind of steady state is called the hyperbolic flow, because if one compute what is the corresponding velocity field associated to that vorticity, the velocity field looks like the following, where the flow looks like these kind of hyperbolic structure near this point, which is a stagnation point. Okay, so why is this steady state important? Well, because if one compute the velocity field when one deviates a little bit from the stagnation point, then so at the distance x1 away, the velocity field will be pointing inwards, and the strength of it is proportional to x1 times log x1. Okay, oops. So what does it mean? Well, in the ODE class, we learned that if we are solving an ODE y prime equal to -y, then y exponentially decaying, right? But for the equation y prime is equal to negative y times the absolute value of log y, then such y would be decaying double exponentially. Right. So for that reason, if one tracks a fluid particle, then the fluid particle would be double exponentially approaching the stagnation point. Right. Of course, this phenomena doesn't directly imply the small scale formation, because this is the steady state. And it's actually a discontinuous steady state where the gradient of omega is already equal to infinity to begin with. Right. So that itself is not a dynamical solution. But the recent breakthroughs in the past decades are about trying to construct smooth initial condition near the steady state such that the solution are retaining the structure of this. Okay, and this was first done by Denisov, where he used this idea to obtain the superlinear growth. And then this was successfully used by Kiselev and Schwerak, where they smooth out this initial data a bit. And so they consider this part of the domain, but set up in the disk, where they used this kind of idea to obtain the double exponential growth, which is known to be the theoretically sharp bound, because for 2D Euler, gradient of the vorticity can most grow double exponentially. However, it seems like the boundary is important for the double exponential growth. And for the torus, currently the world record remains by the result by Zlatosh, where he obtained exponential growth of the gradient omega for the C1 alpha initial data. So these are the results for 2D Euler. And for the SQG equation, more recently, Kiselev and Simin He has considered the SQG setup in the torus, where they proved exponential growth, assuming that the solution remained regular. Here, they have to make that assumption, because for SQG, it's also an open question whether there can be a finite time blow-up. Okay, so these are the small scale formation results for the other closely related equation, Euler and SQG. However, I would like to describe why it doesn't work to extend these ideas to IPM. Okay, so initially we are thinking that, well, can we just try to use a similar idea to extend these techniques to IPM? And soon we realized that it's not possible for the following two reasons. So one reason is that for all these results that leads to exponential growth or double exponential growth into the Euler, they're all based on this Shimon-Bahuri steady state, where they have so they are using the crucial fact that, well, if omega has this odd symmetry, then the symmetry will preserve for all time. Okay. However, for IPM, because of the operator for the Biot-Savart law have the different oddness versus evenness as the Euler and SQG. So it's not the same kind of symmetry will be reserved. So instead of the odd-odd symmetry, this will not be preserved. It's actually the odd-even symmetry. If the initial data is odd in x2, the vertical direction, but even in x1, then that is the symmetry that is preserved for all time. Okay, so this is only one technical reason, I would say. The more substantial reason is that, well, if we want to use the same idea, then we should first have some kind of steady state, could be a discontinuous one, where the particle trajectory are approaching each other exponentially along their trajectory. Right. However, we are not even aware of these steady states. So for example, in R2, one can easily check that the only steady state of the IPM with a finite energy are the boring horizontal steady states where the density are horizontally stratified. And if you plug that into the Biot-Savart law, because it has the partial x1 in front, so it directly corresponds to a constant zero velocity field. Okay, so which means that, well, in R2, there are no steady state, even with a non-trivial velocity field, right? Not to mention whether particles are approaching each other along the trajectory or not. So that is the situation in R2. If we are in the torus, there can be more. However, there's nothing with the hyperbolic flow scenario. So other than this boring horizontal one with zero velocity, there are these vertical stratified steady state with a non-zero velocity. However, if one follow the particle trajectory, none of them will be approaching each other. Okay, so that is the more essential difficulty. Instead of following the previous approach to start from some steady state, so we want to take a really different approach. Okay, so let me start stating the results, and then I'll be explaining where the how the proof is done, which is actually a quite short argument. So let me first state the results in R2. So let's consider any initial data that is smooth, it's compactly supported, it is odd in the x2 variable, and let's say that on the upper half plane, we make it to be non-negative, okay? So then one would do odd reflection into the lower half of the plane. So for any of such initial data, we prove that as long as the solution remains smooth for all time, so during its lifetime where we have a solution, it has to satisfy this estimate, okay? So what does this estimate say? Well, it says that if the solution remains smooth for all time, then this quantity has a finite time integral from 0 all the way to infinity. Okay, so if we're having a certain quantity whose integral is finite over the whole interval, it means that it needs to have certain kind of decay as t goes to infinity in the average sense, right? So for example, 1 over t is like the borderline case where the tail is integrable versus non-integrable. Right. So in that sense, if we are having some quantity whose integral is finite, then this integrand has to be less than 1 over t at infinitely many t at a diverging time sequence. Right. So now notice that this one carries a negative power. So if this quantity is tiny, it means that the HS norm itself has to be huge. Right. So by comparing this integrand with the 1 over t, one immediately gets that if this integral is finite, it means that the HS norm has to be growing to infinity in a certain power, at least so as a power function with the power t to s over 4. Right. So this is true for all the s bigger than 0. We are not sure whether the rate is sharp or not, but the range of s is indeed sharp, which is because when s is equal to 0, this is simply the L2 norm, right? And we do know that the L2 norm doesn't have any growth because it's simply remain conserved when rho is transported by an incompressible density, by incompressible velocity. So in that sense, the L2 norm is conserved, or for any HS norm with s bigger than 0, we show that this HS norm has to grow to infinity if there is a global solution. Okay, so now let me briefly describe the proof, which is quite short. That is our initial data, which is odd in x2, non-negative above and non-positive below, and it's compactly supported. So one can easily check that by the using the Boussinesq law, that this odd symmetry is preserved for all time. And the main tool for our proof is the monotonicity of the potential energy. Okay, the potential energy is simply the density rho times x2. So here for the initial data, notice that rho is non-negative here, non-positive here. So rho times x2 itself is the product of two odd functions. So this thing itself is even. And because the so rho will be always bigger than 0 in the upper half plane, because this horizontal line will always be have a vertical velocity equal to 0. So it means that as long as we have a smooth solution, the potential energy will be always non-negative. Okay, so on the one hand, we know the potential energy is always bounded below. And on the other hand, we show that the potential energy is decreasing in time. Okay, so physically, this is not surprising, right? Because the incompressible porous media equation is basically driven by the fact that the heavier liquids wants to go down, and then the lighter liquids wants to go up. So it makes sense for the potential energy to be decreasing, right? But let's check it. And by the way, this is not our discovery. So the fact that the potential energy is monotone, it was already used in, so for example, in the Elkindi's results before. So if we take the derivative of the potential energy, then a quick application of the divergence theorem give us, this is simply rho times the vertical velocity u2. And what was u2 again? Well, this is our Boussinesq law, and so using that, we have u2 is partial x1 of this bunch of things, right? So we just happily plug it in, and then after we can do the integration by parts to move one x1 derivative to rho, and we also distribute half of the inverse Laplacian to rho. Okay, so after that, we are going to get a negative of a certain quantity squared. So what is this thing here? It is partial x1 rho and h minus 1 norm squared. Okay, so this is something that let's call it delta of t. So that immediately give us the delta is non-negative, and this immediately give us that the energy is monotone decreasing. Okay, so far there is not much math going on, but if you think about it, we have this potential energy which is decreasing, and we also know that it has a lower bound, right? Which means that, well, it can be decreasing so fast, right? If the solution managed to survive for a long time, then when time is very large, the derivative of E is almost equal to 0. Right, so in the sense that, well, this delta is integrable in time, right? And now the key thing is to carefully look at delta, and we are going to get our small scale formation results from there. So delta will be equal to 0 only, so this quantity delta can only be perfectly equal to 0 if rho is a perfectly stratified steady state, which means that rho is just a function of x2. Okay, so however, this is not possible in finite time because our rho is compactly supported at all the finite time. So intuitively, when delta is tiny, this will only happen if rho is almost horizontally stratified, which means that because rho has a finite support, it means that, well, the support of rho has to be stretched into something that is very long. Okay, and then because delta is integrable, we do know that as time become very large, delta needs to be tiny. So rho needs to be very stretched intuitively. And then once rho become very much stretched, we want to show that, well, the vertical, in the vertical direction, it must have very quick variation, and that should be driving the HS norm to be huge. Okay, so far this is just hand-waving heuristics, but the actual proof is not too hard. So it makes use of the information on the Fourier side. Notice that, well, so this is our definition of delta. And now, because we know delta is integrable in time, all we need to show is this relationship between the HS norm and delta, right? So we want to show that if delta is small, HS must be huge in some quantitative sense. And then we, so once we get this, we want to plug it into the facts that delta is integrable, finishing the proof. Okay, so how did we get this key inequality here? Well, this is because on the Fourier side, the L2 norm is preserved, and the L infinity norm of rho hat is bounded. So it means that if this quantity delta, which has this weight here, becomes tiny, then the only possibility is that there is a significant amount of rho hat that is concentrated in the place where this weight is tiny. Okay, so weight being tiny means that because this weight disappears along the C2 axis, so it means that roughly half of the mass of rho star needs to be squeezed into this region here, where the weight is tiny. Okay, but if they are squeezed in there, then because the total support of rho hat needs to be of the same order, because its L infinity norm can't grow to infinity, then it must become very high. But in such case, the HS norm will be huge. Okay, so that is the simple argument on the Fourier side. So similarly, we also have some growth results in the torus and also in the strip, where it's based on a similar idea, except that the growth rate is slightly different due to our proof strategy. So let me skip this proof, because for the rest of the time, let me focus on another topic that I think is very interesting, which is the stability versus instability of stratified state. Notice that, well, for any horizontally stratified state where rho s is only a function of x2, it is stationary. Right, because any such rho s corresponds to a constant zero velocity u, so of course it is stationary. And the natural question is whether it is stable or not, right? So usually we learned that in class that, well, the strategy for us to show whether a steady state for an ODE or a PDE is stationary is that we linearize the equation first. Right, we first find whether this linearized equation is stable or not, and then we try to upgrade this linear stability or instability into a nonlinear one, right? So if we follow that approach, then we would have that the difference between the perturbation of rho and this rho s will be satisfying this equation right there. So after linearizing it, we get that the perturbation eta satisfies this linear equation, where this operator itself is negative, which means that the stability intuitively would depend on the sign of negative G prime, right? Here, G is the profile of the steady state. And it means that if G prime is always negative, then this will be a positive number. So intuitively, we would expect eta to be stable, right? So this has been shown for G equal to minus x2. In this case, G prime is a constant, so that makes the computation easier. Although it is commented in their work that so such arguments can also deal with non-constant G prime of a fixed sign. Okay, so for G is negative x2, which is this again this profile with lighter fluids on top and heavier one on the bottom. So the asymptotic stability for the nonlinear equation was established by Al-Gindi in R2 for H20 and above. And in the strip, it was shown by Castro, Cordoba, and Lear for the perturbation being in H10 or above. Okay, so in our results, we would like to look at the other direction, which is the direction of nonlinear instability. And not only we want this nonlinear instability to hold for a short time in this linear regime, but we also want to have some kind of infinite in time nonlinear instability, which still continue to hold even after the solution has entered the fully nonlinear regime. Okay, so let me briefly mention these two results. The first one shows that any odd, so it's a result in torus, where we prove that any odd in x2 stratified state is nonlinearly stable. So in what sense? Well, in the sense that let's consider any smooth stratified steady state that is odd in x2. And so for any epsilon, no matter how small the initial perturbation is, and no matter how high the Sobolev, the order of the Sobolev norm is, we will show that, well, there will always exist such a tiny, such a rho zero, that's the tiny perturbation in a very high Sobolev space, such that the solution satisfies the difference between the solution and rho s will have all of its hs plus 1 norm going to infinity for all the s bigger than 0. Okay, so it means that for anything that is higher than h1 norm, the difference between them has to grow to infinity with a certain rate as time goes to infinity. So the idea is as follows. So let's say that suppose we consider any odd in x2 stratified state. We want to give it a little perturbation. So first of all, any of such steady state actually is linearly unstable because one cannot have any, there is no monotone density in the torus, right? So for any density in the torus, we are able to identify some point such that locally heavier fluids is on top of the lighter one. And now we grab such a point and we would like to do some local perturbation. The perturbation is run in the way that we used a local rotating incompressible flow to tweak it a little bit. And it's easy to show that there is, when after tweaking it, the initial potential energy is strictly less than that of rho s. Okay, so what does that mean? Well, rho s is the steady state, so its potential energy will stay forever at the same value for all time. And if we are already having some initial state whose potential energy is strictly less than that, then it can only go down as time goes on, right? So in other words, at any future time, there will be always a gap between these two potential energies. Right. So why do we need to use that? Well, because so once we know that the potential energy will always have a gap for all time, it means that the level sets of the density can never become too close to perfectly horizontal lines. So there is a geometric argument that shows that, well, once there is this gap in the potential energy, and on the other hand, the level sets are topologically equal to the level set of rho zero, meaning that, well, it is rho s transported by some incompressible flow, then one can show that, well, this integral can never get too small. It is always bounded below. Okay, and then we relate this integral with delta. So we show that, well, if this integral is bounded below and delta s becomes small, then it's a simple interpolation argument on these Sobolev norms that shows, well, these positive Sobolev norm has to grow to infinity. Okay, so that is the infinite in time nonlinear instability result. So at the end, so I want to also mention another result in the similar flavor. In my opinion, this is the more interesting one. So we look at the situation in the strip, because in the torus, there are no steady state that are horizontally stratified, right? Because one will always, because of the periodic structure, there is always a point where the heavier fluid is on top of the lighter one. But in the strip, there are the stable ones, right? For example, this minus x2, which where the x2 coordinate goes from -1 to 1. And so this has been shown to be non-linearly stable in H10 or above by Castro, Cordoba, and Lear. However, we show that, well, the stability or instability actually heavily depend on which Sobolev norm are we using. So namely, for any steady state in the strip, including this guy that is linearly stable, if we take the perturbation to be in a Sobolev space that is slightly below H2, so the norm can be arbitrarily small, but the important thing is that the order of the Sobolev space has to be strictly less than H2. And then we show that, well, we are able to find such a perturbation such that the HS+1 norm grows to infinity for any s bigger than 0. So namely, the Sobolev, the difference between these two solutions will grow to infinity in any space that is higher than H1. Okay, so in that sense, we showed the nonlinear instability for that solution in spaces below H2, and Castro, Cordoba, and Lear have showed the nonlinear stability for H10 or above, right? So we are not sure which one is the gap between stability and instability, but the important thing is that, well, so the notion of stability versus instability heavily depends on the choice of the norm. Okay, so the idea is as follows. So we cannot use our previous construction because such rho s is already the minimizer of the potential energy among all of its, if we are just transporting it by any incompressible flow. However, we are able to add this tiny bubble here that forms a closed level set at time equal to 0. Okay, so initially, let's say, suppose we are looking at this steady state that is minus x2. So if we look at the gradient in the x2 direction, the derivative is always -1. So if we want the initial data to form a loop here, where it has a point with 0 gradient, it means that in terms of the derivative, it has to have an order 1 change, right? And then Sobolev embedding tells us that, well, if the C1 difference between these two solutions is of order 1, then the HS difference can be made small if S is less than 2, but cannot be made small if S is bigger than 2, right? So that is why our instability result is only for spaces that are lower than H2. And now how are we going to use this little level set here? Well, the closed loop will remain closed during the evolution because it is, so topologically, there is no change, right, to the solution. So it means that for all the time, we can never have something that is very close to a perfectly stratified steady state, in the sense that the partial x1 derivative will have its integral to be always bounded below. Okay, and again, once we have that, this quantity is bounded below, but the h1 or h-1 norm of this integrand is tiny as time goes to infinity. It means that the positive Sobolev norm of this integrand has to be growing to infinity in some way, right? So overall, we want to, because all the previous proof of nonlinear instability in fluids are usually done by linearizing the equation, prove the instability for the linearized equation, and then upgrade it to nonlinear one. But we want to follow, we want to try a different approach that is more of this variational flavor, right? Where we heavily use this monotone quantity, the energy function. And then, so that's our result for the IPM, which the proof is heavily relying on the monotonicity of the potential function, functional. But then one may wonder that, well, if there is no such magic as a monotone quantity, then does the proof still works? Right. So together with Sasha Kiselev and my former student, Jamie Park, we want to see whether a similar approach can be extended to other equations where there is no such magic monotone function. And we are successfully we were successfully able to apply this idea to the Boussinesq equation. It is the viscous Boussinesq equation. So here there is the Laplace mu term. However, there's no thermal diffusivity. So the temperature rho is just transported by the velocity field u. So for such equation in 2D, the global well-posedness is well known if this problem is set up in a sufficiently high Sobolev space. So Ju and Kukavica and Wang has also obtained some upper bound on rho, the H1 norm of rho. So namely, the H1 norm of rho cannot have more than exponential growth. However, to our best knowledge, there has not been any example to show that whether the H1 norm of rho can grow to infinity at all as time goes to infinity. So together with Sasha and Jamie, we try to use a similar strategy, although it's a lot more involved here because the potential energy is no longer monotone. But with the similar flavor, we were still able to show that, well, so one can construct these solutions that indeed have small scale formation as time goes to infinity, namely the gradient of rho. So the H1 norm of rho will be growing to infinity with a certain polynomial rate. Okay, of course, that is still far away from the theoretical upper bound of exponential growth. We don't know whether the best growth is exponential or polynomial, but to our best knowledge, this seems to be the first results that shows the H1 norm of rho in this globally well-posed equation can really grow to infinity as time goes to infinity. So this is a forthcoming work, which we are currently wrapping up, and hopefully it will appear on arXiv soon. So that's all I want to talk about, and thank you for your attention.